Let's talk about rotational symmetry today. We'll start with rotations about the z-axis that we indicate by the operator r hat sub z of an angle phi. We're going to assume phi is a small angle. So r hat operating on psi, our wave function, gives us a new wave function, which we can also write in terms of the old wave function, psi, where we have it as a function of r theta and phi minus little phi. By the same reasoning that we used our time evolution operator, so remember the time evolution operator, t of a we wrote as e, or e to the minus I a p over h bar. We're going to do the same thing for the rotation operator, except of course instead of using linear momentum, we're going to use angular momentum. So by the same token, we can say r sub z of of phi is equal to e to the minus I phi L sub z divided by h bar, where L sub z is going to be the generator of rotations about the z-axis. Little operator of that. So the question is, how do r and p transform under rotations? Let's use rz as a function of delta, a very small angle, and we'll write that as 1 minus I delta L sub z divided by h bar. Substituting in for x, we have x prime is r dagger x r, which we can write approximately as 1 plus I delta L sub z divided by h bar, x 1 minus I delta L z over h bar. We can write that as x hat plus I delta L z. That is I delta over h bar commutator LZ x which of course is I h bar Ly. So this becomes x minus delta I and I away y hat. Similarly, you could do the same thing for y. Y hat becomes y plus delta x. And then, of course, since we're rotating about the z-axis, z and z prime will be the same. Well, we could put this all in a nice rotation matrix and get x hat, y hat, and z hat 1 minus delta, delta 1, 0, 0, 0, 0, 0, x hat, y hat, z hat. So you see, it looks like a rotation matrix, except instead of having cosine theta and sine theta, you have delta and minus delta. But think about it. This is a small angle approximation. And of course, at small angles, with delta small, cosine of delta is 1, and sine of delta is delta. And so this looks exactly like you would expect a rotation matrix to look. So that's rotation about one axis. Now, the question is, can we generalize this to rotations in 3 dimensions? So what we want to do then is go back to the beginning and generalize this to some rotation along some arbitrary direction. We'll call it the n hat direction. If we do that, similarly, we expect that r sub n in this case of phi can be written as e to the minus I phi n dot L divided by h bar. And so we think of this angular momentum as being the generator of rotations, similar to the way that linear momentum was the generator of translations. Any operator that transforms the same way a position operator does under rotation is what we call a vector operator. And so some vector operator, an arbitrary vector operator, we'll call it V prime, is equal to some D, some transformation matrix, times the initial operator. This is what we call a vector operator. So in that case, rotations about the z-axis for any vector, arbitrary vector vx prime, vy prime, vz prime, result from a rotation matrix that looks like cosine phi, sine phi, minus sine phi, cosine phi, and zero everywhere else, times my initial vector vx, vy, vz. So this is how we define a vector operator. This follows from, since we talk about L being the generator of rotations, we write the following way. L sub I commutator with V sub I is equal to I h bar Levi-Civita symbol ijk times V sub k. So this is really the definition of a vector operator, this sort of formulation. Well, operators are classified as either scalars or vectors based on their commutation relations with the angular momentum operator. This sort of encodes how they transform under rotations. But they're also classified separately as either pseudo or true quantities based on the way they commute or their commutation relations with the parity operator. So that would be how they operate under spatial inversion. So let's put a little table on the board and try to indicate sort of a list of how we classify vector operators, or scalar operators for that matter. So let's see, we'll have a true vector, we'll have a pseudo vector, we'll have a true scalar, and a pseudo scalar. So they're all V's. Scalar operator we'll call F. Under parity operation, the anti-commutator of pi, the parity operator, with this vector gives me 0. Under rotation, if I operate with L sub I on V sub I get I h bar epsilon ijk. V sub k is indicated on the right. And good examples of true vectors then would be the position vector or position operator and the momentum operator. They operate in all the same way. The pseudo vector, on the other hand, with the commutator, not anti-commutator, with the parity vector, gives me 0. By the way, anti-commutator, if we haven't talked about this or if you've forgotten, anti-commutator of A and B is A, B minus BA. Plus BA. That's the anti-commutator. And the notation, the swirly brackets. So, in the case of a pseudo-vector, Li, Vi, so this is under angular momentum, gives me I h bar epsilon I j k b sub k. And that, a good example of that is the angular momentum operator. Now, you might think back when you learned about vectors at some point. Anything that results from a cross product, we call a pseudo-vector. And notice that angular momentum is one of those quantities that results from a cross product, in this case R cross P. So this may be somewhat familiar to you from what you've learned before. Well, how about the true scalar? In the case of a true scalar, parity operator operating on some scalar operator f gives me 0. The angular momentum operator commutes with the scalar operator, so that gives me 0. And good examples of that would be something like R dot R. So that's what we call a true scalar. And then finally, a pseudo-scalar under parity, in this case the anti-commutator of the parity operator in F gives me 0. With angular momentum, this gives me 0. We don't really have a concrete example of a pseudo-scalar concrete quantity, but anything that results from some operation like A dot B cross C is a good example of something that would result in as a pseudo-scalar. So RP and L are vector operators, and so that's going to be such that, let's do it this way, Li Rj gives me I h bar epsilon I j k R sub k. For momentum, for P, I get Li P sub j commutator gives me I h bar epsilon I j k P sub k. And then finally, of course, Li Lj gives me I h bar epsilon I j k L sub k, as you did much earlier. All stands here. It all follows logically. A scalar operator also is a single quantity that's not changed by rotation, so it should commute with L. So we expect for any scalar operator, Li F commutator should always be 0. So basically, we classify operators as either scalars or vectors depending on their commutation relations with L, and true or pseudo based on their commutator relations with the parity operator. Let's move to continuous rotations. So for continuous rotations, I want to look at rotational symmetry for continuous rotations. If the Hamiltonian is rotationally invariant, in other words, if V of R is equal to V of scalar R, so it's a central potential like the hydrogen atom, then the Hamiltonian commutes with any rotation by any angle about any arbitrary axis. In other words, what that's saying is my Hamiltonian operator commutes with R sub n, any arbitrary axis of phi. This must also work for any infinitesimal rotation. So if I write R of delta, a very small rotation, as approximately 1 minus I delta n dot L divided by h bar, we expect that h is going to commute with the three components of angular momentum. So again, we expect h and L commutator to be 0. All that combined tells me that for a central potential, by Ehrenfest's theorem, then the time derivative of my angular momentum operator, I could write as I over h bar times the expectation value of the commutator of h and L. Since this is 0, this tells me that the time derivative of angular momentum is 0. That tells me that the angular momentum is constant. So what this is telling me then is that the symmetry, the rotational symmetry, implies a conservation of angular momentum. Once again, Noether's theorem holds in that for a given symmetry, we have a given conservation, a conservation law. So what we get from this is that my Hamiltonian, my LZ, and my L operator, my L squared operator, form a complete set of commuting observables for bound states with a central potential. So pairwise, we can say H L squared commutator is 0, H L Z commutes, and of course H L Z L squared also commutes. So eigenstates of the Hamiltonian can also be chosen to be simultaneous eigenstates of L squared and LZ. What that means then, H applied to wave function psi n Lm, that's equal to E sub n, the Schrodinger equation. LZ applied to psi of n, L, and m gives me m h bar, psi of n, L and m, and of course L squared applied to psi n, L, and m gives me L plus 1 h bar squared times psi n, L, and m. So the quantum numbers n, L, and m uniquely specify a bound state of the Hamiltonian. Examples of this, of course, we've seen already: the hydrogen atom, the harmonic oscillator, the infinite spherical well. Good examples all. We might think about the case of what happens when we have eigenvalues that correspond to where we get the same energy eigenvalues for different eigenfunctions. And so what that brings up is the concept of degeneracy. Now, as I mentioned in the statistical mechanics class, degeneracy is used in a number of ways in physics. We talked about degenerate Bose gases and so on. That's not what this is. This is different. Most degeneracy in quantum mechanics is based on symmetry. Sometimes we have a situation arise, we say it's by accidental. It's an accidental degeneracy just by coincidence, but generally speaking, if you look hard enough, you might be able to find some symmetry underlying even that. So if I have a case of symmetry, the implication is if I have some arbitrary operator Q, it commutes with the Hamiltonian. And so if we have a stationary state, we call that psi sub n, then I would expect that if I operate on Q, on psi sub n, I'll get some new stationary state, psi prime of n. That should also be a stationary state that has the same energy. So that would be a degenerate state, two different eigenfunctions, two different eigenstates with the same energy. Can we prove it? Sure. Watch. I can write this as H times Q. I'm going to apply H to both sides, psi of n. And that's the same thing as QH applied to psi of n. Since these guys commute, H applied to psi of n is just E sub n. And so E sub n Q applied to psi of n is going to be equal to E sub n psi of n prime. So an example of this, if I have an eigenstate of a spherically symmetric Hamiltonian, and you rotate the state about the same axis, you're going to get back another state, but you're still going to have the same energy. Now, just because you have continuous symmetries doesn't mean you're always going to have degeneracies. For example, psi sub n and psi n prime might be at the same state. Good instance of this is the harmonic oscillator, where when I rotate, you either get even or odd states. And so if I act on one with a parity operator, I'll get the other. But that doesn't matter. That's essentially the same state. So we don't say that the harmonic oscillator energies are degenerate. On the other hand, if there's only one operator that commutes with the Hamiltonian, let's call it Q, you're not going to get degeneracy. However, if you have two operators, both of which commute with the Hamiltonian, but don't commute with each other, then you absolutely will get degenerate states. It's inevitable. So, for example, Lx, Ly, and Lz all commute with the Hamiltonian, but they don't commute with each other. Therefore, you're going to get degeneracy. You just can't help it. I'm going to do an example of this when we pick this up next time.